All right, guys, we're continuing Chapter 3, Part 2 PowerPoints. I left off the last video on slide 6, which I introduced the single replacement reactions, and then I mentioned the activity series. I just want to finish that topic up real quick, where basically the example we just looked at, we added copper to silver nitrate, and basically we said silver nitrate, that compound was aqueous, so it was in solution. When I drop the copper in, if the copper wants to get into the solution and start dancing around, he has to kick the silver out. Okay? I could also, the second reaction I have written here is the same idea, but now I have copper nitrate in solution. So this time copper is already in there, and if I add silver from the outside, now silver wants to go in and kick copper out. Okay? So the idea is here, both these reactions can't work. It's along the lines of, if you go to school one day and, a bully comes up and, grabs you by the shirt and says, "Give me your lunch money." If you're a weak little kid and, you're afraid of the bully, then you might give him your lunch money and say, "Here you go, don't hurt me." Okay? But then the next day, if you walk into school and you walk up to the bully who's huge and bigger than you and stronger and everything, and you grab him by the shirt and say, "Give me your lunch money," chances are the bully's probably not going to give you his lunch money. He's probably going to tell you to scram, if you're lucky, and let you go. So the idea is, with every combination of two metals, the reaction is only going to work one way. Either copper is strong enough to kick silver out, or silver is strong enough to kick copper out. One way is true and not the other. The only way we know is by looking at what I mentioned in Chapter 4, the activity series. That's a ranking list to see who the biggest bullies are. The ones at the top are the ones that are the strongest. They're the ones that can kick out any other metals that are beneath them. Okay? So if I look at this reaction and I look at these two metals, if on the activity series, copper is higher on the activity series than silver. So that means that copper, if it's added to a solution that silver's in there, copper can walk in, tell silver to get out of there, and the reaction will actually work. If I try the second one, where silver walks up, and silver's the wimp, if silver walks up and tells copper to get out, basically that's never going to work. Only one time in history has that ever worked, where the wimp was able to fight back and beat up the bully. And so in this case, silver cannot displace copper. So in that case, I'm going to put no reaction, because basically when that happens, silver, when I drop it into solution, it's going to sit on the bottom of the beaker and not do anything. The only time in history that the wimp has ever beaten up the bully was in the original Back to the Future movie. If you haven't seen it, you should go watch it. Anyway, so that's our single displacement reactions. Everybody know George McFly? That's the guy. All right, so that moves us on to our next topic. Our next type of reaction is double displacement. So each of these reactions, we want to be able to recognize them, because what's going to happen in this section is that if I give you a possible reaction, what I'm going to do is I'm going to give you the reactants and just say, hey, here, if I give you these reactants, tell me what the products are going to be, and you have to come up with the products on your own. By learning these types of reactions, it's going to show you patterns that you can look for, so that you know, if I mix these two things together, that's going to be a single displacement reaction, or a double displacement reaction, or a combustion reaction, or whatever. Okay? So you have to look for certain telltale signs in your reactants, like what they look like, to help you determine what kind of reaction it's going to be. So if we have a double displacement reaction, it's going to look like on my reactant side, on the left side of the reaction, it's going to be two ionic compounds. Positive, plus minus for my two compounds. So AB, it might be like sodium chloride, Na plus and Cl minus. The other compound might be magnesium hydroxide, Mg plus 2, and then OH minus, right? So the two compounds, if they're both ionic compounds, that's going to tell me, oh wait, it's going to be a double displacement. If I go back to single combustion, combustion is always going to be some compound that can be burned with O2. If you see something plus O2, then you should be thinking, excuse me, you should be thinking that maybe that's a combustion reaction. And then finally, single displacement, you're going to have one element by itself, and then you're going to have an ionic compound. That's my two reactants. Okay, so those are kind of the things that you'd be looking for to set up the patterns so you know how to treat a certain reaction. All right, so what happens in double displacement, again, if I go back to that old school example of dancing couples. So double displacement reactions usually happen in solution. So in my examples, when a compound's in solution, the elements of the compound are kind of dancing with each other in the solution or whatever. They're moving around in the water, all that kind of stuff. So double displacement reactions usually happen in solution. At least one of the compounds is usually dissolved, and then the other one is, sometimes they're both dissolved, sometimes you're adding one to the other. But what's going to happen is my couple on the dance floor, they're going to swap partners. Again, we're going for the old school sexist approach where usually I would say if it's a boy and a girl, and traditionally the boy leads in the dance, so I typically say the boy is the cation or the positive ion, and the girl is the negative ion. I'm not saying girls are negative, so don't start thinking that. But positive, negative, positive, negative. And then if they switch partners, typically this boy will run over and try to dance with this girl. So A ends up going with D to make AD. C goes with B, but specifically the cation has to go in front. So don't write BC when you get your product over here. The cation or the boy has to lead. So my new compound here is going to be CB. When I make my new compounds, again, I have to check charges to make sure I put them together in the right ratio. Because the ratios I had on the left side are not necessarily going to be the same as the ratios I have on the right side. You always have to double check that. So, an example. My first compound, AB, silver nitrate. And again, you have to see AB, that's positive ion, negative ion. Either one of those might be a polyatomic ion. So you have to recognize your polyatomic ions really well. Okay, so Ag plus, NO3 minus, and then my other compounds, Na plus and Cl minus. When I put them together, Ag ends up with Cl. So there's my AgCl. Silver's plus 1, chlorine's minus 1. So when you write that, double check to make sure the formula works. And then Na goes with NO3, so NaNO3 is that. Now, the physical states, this is the part that crosses over into chapter 4, where normally the question will say, I mixed together a solution of silver nitrate, and if I say a solution, you know it's aqueous. I mix it with another solution of sodium chloride. So I know my two reactants are both aqueous, and when I mix them together, then it's going to say predict the products. So you have to figure out what the products are, and then you also have to figure out what their physical states are. All right, so when you get to the products, you repair them the way the pattern says, and then to predict which compound's aqueous, which one's solid, in chapter 4, there are the solubility rules. It's the set of rules to decide which compounds are soluble in water and which ones aren't. Okay? Again, I know I'm in chapter 3 still, but you can start working on that now. You got to figure those out. Again, this semester, when you're working on your homework and your online stuff, and if the test is online, I'm going to let you use your book and let you use your notes, but you're not going to have time to find everything that you want. Okay? In normal semesters, you have to memorize the solubility rules. You have to know that for sodium nitrate, there's a rule that says all ionic compounds that contain an alkali metal which is a group 1 metal, all ionic compounds that have group 1 metal are always soluble. So any ionic compound with sodium, I know it's going to be soluble right away, based on that rule. There's another rule that says any ionic compound that has nitrate in it is soluble. So that's another rule that you can go by. So this one, either rule, if you know one of them, you would know that this is a soluble compound. If it's soluble, that means if there's water anywhere present, which aqueous solutions tells you that everything's in water, this compound, when it forms, will stay dissolved in the solution. But then silver chloride, that ionic compound, the rule that you have to learn, chlorides are mostly soluble except when chloride pairs up with silver, mercury, and lead. So when silver and chloride come together, that's an exception to the rule. Most chlorides are soluble, but this one is not soluble, which means it's going to come out of the solution, which is called precipitation. It's going to form a precipitate, which is it's going to form a solid on the bottom of the beaker. So that's why I put the S there. All right, so that's what I have to look for here. Now, when I mix ionic compounds together, two ionic compounds, A, B, and C, D, okay? When I mix them together, you could always swap partners and act like something happened. But in reality, just because I mix stuff together, reactions don't happen all the time. There's specific things that we have to look for, okay? So, with a double displacement reaction specifically, one of three things has to happen. Either one of the products has to form a solid, which is a precipitate, or one of the products has to give off a gas, like carbon dioxide, or when we repair them, if I have like one of them has a hydrogen in the front and the other one has a hydroxide in the back, when you repair them, if it makes a water molecule. If the reaction forms one of those, then it really is a reaction. If the reaction doesn't form one of those, then that just means you mix two things together. They mix with each other, but they didn't react. Nothing significant happens. For a double displacement reaction, these are the only three things that we would consider to be significant. Okay? So, again, we're going to practice that more when we get to chapter 4. So we'll leave it for now. Now, a specific example of a double displacement reaction. Well, I said it's always two ionic compounds. One that goes a little bit past that, instead of having one of the ionic compounds, it could be an acid, like HCl. It's not technically an ionic compound, although the hydrogen is H plus and the chlorine is Cl minus, so it's kind of like an ionic compound. But if I mix together an acid and a base, they will react, and this is where on the previous slide I said you have to form either a precipitate, a gas, or water. Well, if I mix an acid and a base, the hydrogen here, the hydroxide here will form a water molecule. Even though when I look at this one, I'm not going to see a visible change occur, because like if I form a precipitate, I'm going to see the whole solution turn cloudy. If I form a gas, I'm going to see bubbles coming out. If I form water in an aqueous solution, I'm not going to be able to tell. Okay, so that is an example. That would be an invisible reaction. Now, I will say it's exothermic, so if you feel the container, it'll get warm. But you're not going to actually see any change that occurs. And a lot of people in high school, when they took chemistry, I mean, sometimes people learn a lot in high school, sometimes they don't. But a lot of people remember anytime you mix an acid plus a base, you get a salt and water. Do you remember a salt? This NaCl is called table salt. It's the most common salt that we see, but actually a salt is any ionic compound. Any ionic compound is a salt, okay? There's table salt, there's Epsom salts, there's rock salt. They all have different chemical formulas. There are lots of salts out there. There are salts that are soluble, there are salts that are insoluble, okay? So any ionic compound is called a salt. All right, so real quick, our last one we'll probably get through in this video. Synthesis, which I mentioned, can also be called addition or combination. Basically, we take two small things, put them together to make one bigger thing. Okay, it could be mixing two elements. When you mix them together, if they react, you can form a compound. So you're combining two small things to make a bigger thing. It could be you mix an element and a compound. When you mix them together, you make a bigger compound. It could be you mix a small compound and a small compound, put them together to make a bigger compound, right? So they're different appearances, but anytime you have two things that combine to make one thing, that's going to be a synthesis reaction. Oh, but it's not balanced. There it is. All right, and then last one, real quick, decomposition is very similar to synthesis, it's just backwards. With decomposition, I'll have one compound or one reactant, and it's going to break apart into smaller pieces. It might be it breaks into elements, it might be that a big compound breaks into smaller compounds, it doesn't matter. If one thing's breaking into pieces, that's what we call decomposition. Again, all these are just kind of general things to look for. I would say combustion, single displacement, and double displacement, those are the ones that you should be very good at predicting the products. Combination or decomposition, or synthesis and decomposition, those are a little bit harder to predict what's going to happen unless you are given more information or if it's just a really simple reaction. Like hydrogen plus oxygen yields water. That's simple enough that if I say mix hydrogen and oxygen together, you probably should know that you make water. But if it gets any more complicated than that, then you probably don't need to know. So our quick example, sodium chloride, if you pass electricity through it, you can actually split it back into the two elements, so you are decomposing that reaction. Cutting off, going to the next video.